Good morning, everybody, and welcome to Bird on behalf of me and all the others that haven't been spoken yet and will. But I want to thank Jan for setting us up for this great discussion about how important and integrated this topic is. I want to thank Lonnie for that incredible overview of the challenges we face in climate and also the legacy that the researchers here at the Bird Polar and Climate and the Institute of Polar Studies has had in building that understanding. Implicit in the dual challenges that Lonnie just laid before us, that we have to learn how to better relate with each other and with the planet, is an appreciation for the irreplaceable planet that we do have and our collective responsibility for stewardship. So there's many ways to express this, and astronauts have been great at it. They're moved to wisdom as they gaze really in awe. And remember what awe is. Awe is both terror and amazement. Terror is they're in a tin can above this, and realizing that thin atmosphere that sustains all life as we know it and all evolution to this point as we know it, our celestial home. That's the way they put it. And the point here is that we're citizens of this world, and the collective sense of taking responsibility is implicit in this study that we go forward in. But my job today is really to speak as a steward of climate information. That's kind of the mantle we wear as the State Climate Office. To sort of be a signpost to the many ways in which researchers are tackling the physical science of understanding this incredible system. Because that amazing blue planet is full of dynamic processes that integrate life, that integrate the ocean, that integrate the lithosphere, and then the atmosphere. And of course, it's all driven by the sun. And the first two principles of essential climate literacy that are put forward by NOAA and by the AAAS and maintained by our own US Global Change Research Program states basically that the sun is our primary energy source, and that what we see in the climate is an expression of the balance of energy through all sorts of fluxes in this incredible system. So climate scientists really had to tackle that. Now, in this context, when I teach the class of global climate change, I always like to remind everybody that the greenhouse effect is 100% natural, and not only that, it's 100% essential for maintaining water in all three phases at the normal range of temperature that we experience on the planet. Life relies on this greenhouse effect. And that balance of energy of incoming solar and the outgoing long-wave radiation mitigated by that thin layer we call the atmosphere is essential. So what we're doing when we load up more greenhouse gases is enhancing this effect and causing problems. And so going forward and looking at this as scientists, I'm just going to play a little spool here of the net radiation term. It reminds us that our radiation and our energy source is not evenly distributed latitudinally. Okay, and we have this net incoming radiation that's more intense at the lower latitudes. The outgoing radiation going out everywhere at the same time leaves us with this deficit that sets up the dynamic for general circulation of the atmosphere and the oceans. But it's a very complex system, and you can see the schematic over here reminding us that we have to account for fluxes of energy and mass or momentum between the atmosphere, the cryosphere being this interesting mitigator, which we have a certain passion for here at the Bird Polar and Climate Research Center, but the ocean and the land as well. And if we look at that blue marble and keep that in our mind, it's wonder why we call this planet Earth. Why isn't it ocean? So energy balance is the theme here. And the methods that are employed are really to try to better understand all of these fluxes, to observe, monitor, and measure, model, to simulate and predict, and to synthesize data on this amazing planet over multiple scales of space and time. And what I've shown here in the upper right is an image of the fever, okay? And I really encourage you to get online and check this out in real time. You can go and zoom in on our webpage there and check out the fluid Earth and all of the dynamics, and you can look at time and see how you can pull up different fields of temperature and momentum and stuff. Do that. I'm not going to take time to do that here. But it gives you an appreciation for the way in which we can visualize and tackle this. But the way scientists have to look at this system that's complex and interrelated is by modeling it. And we have great modelers here. The biggest users of the Supercomputing Center at Ohio State are David Bromwich. And I put Aaron Wilson up here because he provided these slides. But these guys are integral to the group called Polar Meteorology that optimizes dynamic numeric models, uses large gridded climate data sets, supercomputing resources, like I said, and solves and addresses multiple problems of climate and weather on different times and space scales. As an example, this is highlighting in on the blended reanalysis data set that they put together for the Arctic that takes observations and models and comes up with an interpolation over a grid to look at this polar amplification of warming and some of the insights you can get through careful experiments with models. Another way in which the dynamics of energy are moved and transported through both the atmosphere and the oceans is tackled by Zhengyu Liu, who's our Max Thomas Professor of Climate Dynamics in the Atmospheric Science program over in Geography. You can sit there, Brent. Take my seat. And his models are also highly computationally intensive and works with NCAR to do this. But some of the questions he's tackling are really important. What will happen to the future of Atlantic overturning circulation as we warm up the planet? In a recent paper, he tackled this and actually reassessed how AMOC is slowing down, and the model projections may suggest that it's in danger of collapse, and maybe that there's some bias implicit in the models that look at stability rather than the uncertainty. So although the movie The Day After Tomorrow might be all sorts of fantasy for its timescale, he might say, well, maybe we should think about the decade after the next decade instead of the day after tomorrow. He's also looking at heat transport and the transit response under anthropogenic warming in a paper that just came out with his graduate student, Cheng Fei. Looks at this question of what will happen to both atmospheric and oceanic heat transport, and there's a lot of wiggly, squiggly lines here. But under global warming, what you can see is that there's interesting intensification of the atmospheric heat transport, where the ocean heat transport seems to reduce. But it's only by tackling this with really computationally intensive and coupled models of the atmosphere and the ocean that we can get some answers here. What they also do is extend this through time all the way to 21,000 years ago when we had glaciers a mile thick sitting over here in Columbus, Ohio. Okay, and running transient models to look at how the climate has changed over this time, and also using important tracers like isotopes to run through that model. Stephen Quiring is another professor in geography and atmospheric science, and he does a number of different studies that also use a lot of data-intensive analyses. And he does some interesting machine learning and artificial intelligence to look at how we might better predict power outages. So very practical applications for the atmospheric dynamics here. But he also is thinking critically about land atmosphere dynamics and our deficit of observations for drought and what that might look like. Jialin Lin, associate professor also in atmospheric science and geography, has done a lot of really careful work looking at data observations and model output, specifically around the tropics, to think about the redistribution of energy through ENSO and other semi-periodic fluxes, to look at feedbacks in the climate system. How do clouds intercede and change the fluxes of energy? Alvaro Montenegro is the current director of atmospheric science, and he is doing some really interesting stuff when it comes to dynamics. He's trained as an oceanographer, but now as an atmospheric scientist runs some models and simulations of things like people and boats populating Sumatra, thinking back tens to hundreds of thousands of years ago. And then species change. These are actually fish, and these are actually literally hot off the press of two master's thesis work that I'm gonna have to go attend to defenses later this week. Jay Hobgood looks at a different time scale of very dynamic storms, the tropical storms. Keep in mind, this is an image over here of Idai that just ravaged Africa. And so take a look at his web and blog. He does an amazing job documenting tropical storms, and he's quite a good Twitterer. And there's his handle over there, Jay, the blue jay, and Hobgood with the Saphir-Simpson warning. The Glacial Dynamics group right here at Byrd Polar and Climate Research Center has taken observations to a new level, literally to space, and using those images, getting a three-dimensional view of our cryosphere and its dynamics. And these amazing digital elevation products have given us new insights into Greenland's ice sheet dynamics, and there's a great slide that Michaela put together from her thesis work. It's spooling through to give you this mass balance flux that's unprecedented. And also just looking at the surface elevation changes with DEMs at 2-meter resolution, you can look at changes in lava flows and dynamic responses, even deforestation at the high latitudes. I was told to wait as I press these buttons. There it is, polar biogeography, and this is Joel Barker. He unfortunately couldn't be with us because he's teaching today, studying the biogeochemical processes in the frozen environment, going underneath the West Antarctic ice sheet in the SALSA project to look at how stable or unstable this ice has been over time, carbon fluxes in the Arctic environment, as well as deposition of black carbon and its impact in the cryosphere. Liz Griffin, I don't know if she's here, but she has a poster, so check hers out. She's doing interesting work on thinking about carbon balances over millions of years. So when she's talking about the Eocene here and the hypothermal events, this is going back tens of millions of years ago to think about analog situations of rapid carbon output and what that might mean. The paleoceanography group, right here on this floor around the corner, if you want to go tour their lab, takes proxies of microfossils in marine sediments and is able to reconstruct ice histories of the Arctic. Really important in our energy balance situation. And you can see how they can use sediment size to look at currents as well. And then when it comes to the ice core group, Lonnie didn't get a chance to talk much about what they do here, but it's an amazing record, almost unprecedented in gathering multi-proxies to look at temperature, atmospheric chemistry, net accumulation, dustiness, vegetation changes, volcanic history, and of course those important bubbles of gas that gives us a long-term history of greenhouse gases and therefore anthropogenic emissions. This is a wonderful place, and we owe tribute to the Calcaya ice cap in Peru. Okay, this is where Lonnie has a great story about persistence and creativity in science with a low budget, and just really, he told me once that science is like 99% persistence and 1% inspiration. So listen to his story about going here with just a short end of the NSF budget and starting a whole entire career that sustained multiple livelihoods right here in Bird. But look at the edge of this ice cap and appreciate the high resolution detail you can get in the low latitude setting, which is very close to civilizations. And what we can look at is how this couples with the archaeological record and see how availability of moisture and water actually seems to correlate with changes in settlements, whether they're up in the highlands or down at the coast. I also am compelled by this environment. I find no better landscape than the Andes to look at this coupling of human society and the environment that these people have adapted here for millennia. But what we've been looking at is below those ice core sites, what's happening to the glaciers and what's the contribution of that water to streams, and how do we get a handle on that when we don't have good observational data? So using a mix of chemistry and embedded instruments and now tree rings, some of my students have been able to innovate and get a lot of embedded look at different scales of operations and thinking about quantitatively assessing these fluxes. I would give a shout out to Forrest and his mountain drone team for their innovations in UAVs, unmanned aerial vehicles, which are great at getting high resolution data here. And then also in the Great Basin National Park, we've had students, including undergrads. I want to shout out to James White, poster number 24. Go check this out. He's a dual major with earth science and atmospheric science. He's graduating and he's going to be making some big impacts. So check out his fire history, came out of a core that we got in the Great Basin National Park, but also Emily Sambuco, who's taken a great care in looking at all these embedded low-cost monitors of temperature and humidity strung in trees throughout this elevational gradient in the park. Jim Staggy is an engineer, but he's also thinking about tree rings. And he's really good at hydrology and thinking about how to couple and assimilate these data sets across time and space to get at really important questions of drought impact and water management. Gil Borer, I saw just walk in here. I saw his beard. There it is. Eco-hydrology and hydrometeorology, another engineer. And I think the synergy of engineering and climate is really critical as we go forward if we think about these dual challenges Lonnie left us with. But here we have measurements of carbon fluxes on multiple scales and thinking about movement and dispersion in the atmosphere, some very good integration of modeling and data assimilation. So I want to come back to this image of the blue marble and leave us with a thought. Science is really important. What we know and how we figure it out about this planet are fundamental. But I don't think we can go forward to get these challenges without balancing those questions with what ought to be going on in our planet, the ethical dimensions, and then what do we actually do in the practical sense? We're in this together, like it or not. We can't just remove people we don't like from this equation. We have to embrace the foibles of human behavior. And that is a critical factor. Science is a human endeavor. And so just borrowing from some images here by Cal DeWitt and Malcolm Pugliani, who realized the irreducibility of some of this complexity is lost when we funnel in and we stand in silos. And we have to actually resist that. Okay, as researchers and academics, there's a tendency and there's a whole business behind separating us, but we need to come together. And I think Bird offers a great node for that, whether you can get here yourself or touch base once in a while to go forward to meet these challenges. So thanks very much. I look forward to interacting more.